Churchill. It's a pleasure to talk here. Very grateful for the invitation, and it's wonderful that you have all set this up. The first question is, can you hear me and see the screen?
Yes, we see the screen and we hear you very, very well.
Good. Yes, so I'm going to talk about the second coordination sphere in organometallic chemistry. To begin with, this looks like a rather narrow topic compared to some of the speakers, but the principles apply universally across chemistry. So I hope you will take away some of the principles, whatever your speciality is. So first thing is to say what I mean by the first and second coordination sphere. I've drawn here on the left a molecule of ruthenium with 4 phosphines and 2 fluoride ligands. And the blue sphere is what we call the first coordination sphere or the inner sphere. And the yellow outside it is what we call the second coordination sphere or the outer sphere. And here I've drawn 2 hydrogen fluoride molecules, hydrogen bonded to the ruthenium fluorides. So in this sense, the HF is in the second coordination sphere. Now, we can also have interactions in the second coordination sphere between 2 molecules if they are complementary to one another. So at the right, I've drawn 2 complexes with nickel fluorine bonds, and this benzene ring has 4 fluorines and most importantly an iodine on it. And the iodine is perfectly set up to form an interaction with the fluorine from the next molecule. This is called a halogen bond. I'll explain more about them later. So we say that these two, this molecule is self-complementary. So it can interact directly with another of the same molecules. So I will show you some more examples of both this one on the left and this arrangement on the right. In addition, I want to mention interactions within the first coordination sphere, but between the ligands of that coordination sphere. So this time we have an iridium complex. It's again got 4 trimethylphosphines and a hydroxide ligand and a hydride. And there's an interaction between the hydrogens, the OH as the delta plus, the hydride as the delta minus, and the result is that the iridium oxygen hydrogen angle is rather narrow, and these 2 hydrogens approach one another. And you can see that by neutron diffraction. Neutron diffraction is the best method of getting the positions of the hydrogen atoms. So this is one of the first examples of what we call now call a dihydrogen bond. It wasn't called that then. This is 1990 and is a Milstein complex. And Bob Bow was the neutron diffraction person who really did a huge amount for molecules like this. Now, so this second coordination sphere, I've already mentioned hydrogen bonds and dihydrogen bonds and halogen bonds. So those 3 already mentioned. And I will also talk about interactions with sigma complexes. And if you don't know what they are, I will explain that in due course. other interactions I'm not going to talk about today, the pi stacking or van der Waals interactions, but they can be very important too. If you want to persuade anybody that van der Waals interactions matter, I think about the gecko and how it walks on the ceiling. That's all down to van der Waals interactions. So that's a perfect example to explain to people. Now, usually these interactions in the second coordination sphere have energies of less than 50 kilojoules per mole. Indeed, 12 kcals, a good deal less, but that's not always the case. Usually we're talking then about weaker interactions. So what would you like to know as a chemist about these secondary bonds? Well, there are a lot of questions you need to answer, and I certainly won't answer them all today, but I'll touch on most of them. First of all, you know how to detect them, both in solution and the solid state. We've already mentioned neutron diffraction. We need to understand what the structural consequences are of these interactions. We need to know how much bond energy there is for these. And one of the characteristics of weaker bonds is that we get dynamic rearrangement. So we can study those dynamic rearrangements, and they have implications themselves for the reactivity and the catalysis. And of course, those are probably the most important questions of all. We can also use the interactions to build much bigger structures. And the MOFs that Omiyagi talked about were not held together by hydrogen bonds, but many of them are. So that's another area where we have great influence. So we're going to start with the hydrogen bonds, the dihydrogen bonds in the ligand domain. So what I mean by that is explained on the next slide. The ligand domain was a term that was started by my colleague Lee Brammer, and how he defined it is where the metal and the ligand atoms are in strong communication. So here we have a metal X bond. The X is polarized delta minus interacting with a hydrogen bond donor BH, and that's the delta plus. But it might also be a more extended system where we have the XY there, and I should have moved the delta minus along, I see. A dihydrogen bond is a different sort of hydrogen bond because the delta minus, the Lewis base, is a hydride. And so we have MH delta minus interacting with BH, and here's the delta plus. This is called a dihydrogen bond. The term was first used by Bob Crabtree and Odile Eisenstein, but also Bob Morris, for instance, played a crucial part in understanding the principles. So what sort of molecules can we look at to see the importance of the hydrogen bonding? Well, I've put at the top metalloproteins, and I'll illustrate that in a moment. Crystal engineering, that relates to the MOFs, for instance, but is a much wider aspect. Supramolecular chemistry, you heard about that from Jean-Marie Lehn. Homogeneous catalysis, of course. Perhaps less well known is that the reagents used for metal extraction are often based on hydrogen bonds. So let's have a look. I've put on two examples of metalloproteins. The first is a classic where I have a family interest. This is hemoglobin and myoglobin. Here we have the iron surrounded by the porphyrin, and there's the O2. And the O2 is hydrogen bonded to a histidine. So that's called the distal histidine because it's a little further from the iron than the histidine that is directly bonded to the iron, and that's underneath in this picture. So the dioxygen to histidine hydrogen bond is critical to the behavior of these oxygen carriers. On the right here, I've shown hydrogenase. This is the iron-iron hydrogenase, and the crystal structure comes from Fontacilla camps. And here we have an iron cyanide, a cyanide complex, and the cyanide nitrogen is hydrogen bonded to the NH2 of a lysine, and this forms part of a hydrogen bonded chain which goes right to the outside of the protein, and this is one of the ways in which the electrons and the protons are transported. Hydrogenase, you remember, hydrogenases can either convert H2 to H plus or H plus to H2, either way round. So those are two examples from metalloproteins. Now, I said earlier that most of these hydrogen bonds are weaker than 50 kilojoules per mole, but I want to mention the exceptions. These are called symmetrical strong hydrogen bonds, and the classic example is the bifluoride or hydrogen fluoride ion, FHF minus. It's perfectly centrosymmetrical and is the strongest known hydrogen bond. I looked up modern calculations and experiments, and they come out at about 190 kilojoules per mole. So it's this is 43 kilocalories, if you prefer that, and that's for the energy of dissociating FHF minus to F minus and HF. So we can't always measure the bond energy, but look at that FF distance as a reference point, 2.26 angstroms. Now, look at this complex, which, unlike FHF minus, contains two metals, two iridiums, and now we have an OHO bridge between the two iridiums. And if you look at that expanded here, what you see is that the OO distance is 2.39 angstroms. Oxygen is a bit bigger than fluorine anyway. It's not that much longer than the FF distance, and it's again symmetrical. The black, by the way, is the experiment. The blue is the calculated distance. So this comes from the Bob Crabtree and Odile Eisenstein. Now, this molecule is actually a mimic, in a way, for the transition state for transfer hydrogenation. Transfer hydrogenation is a very important reaction done commercially on quite a big scale, and we'll probably hear more about it as over the coming days. And it involves outer sphere interactions. So this is a sort of mimic for how it works, where we can actually see something that resembles the transition state. Now I want another example of, this time with a dihydrogen bond in catalysis, and I've chosen as an example the electrocatalytic oxidation of hydrogen. Now, this is a process that lots of people are working on. particularly as a way of using renewable energy without using platinum group metals. This example comes from Maurice Bullock and Dan Du Bois, and you probably can't read this cycle at the moment, but I'll show you in more detail soon. This is a very low overpotential, that's to say a low barrier to reaction with this catalyst involving iron. If you look at hydrogenases, they have almost no barrier at all, no overpotential. Most of the synthetic examples have very big barriers. So let's have a look at a couple of steps where we see the detail. And here at the bottom left, we have the hydrogen coming in to bind to the iron. And it binds as a dihydrogen complex. And the ligands, we have a chelating diphosphine, but there are two pendant nitrogen units attached. And what happens next is that the HH bond cleaves to form an iron hydride and an NH. So it cleaves heterolytically, but what remains is that interaction between the H minus on the iron and the H delta plus on the NH, the dihydrogen bond. So that plays a critical part in catalysis. And then with an incoming base, the proton can be removed. So this mechanism is not plucked out of the air. It's backed up by the isolation of both of these complexes, by dynamic NMR of the exchange processes, by deuterium labeling, and by electrochemistry. So if you want to understand how all of this fits together, I strongly recommend this paper by Bullock and Co. So I want to move back to metal fluoride complexes, and I mentioned them at the start in my initial example. And one of the reasons is that they're very good for hydrogen bonding. And the other aspect that I want to show you is that thanks to 19F NMR, we can quantify the energetics of interaction. And we can compare the energetics to those of ordinary hydrogen bond acceptors that are typically used by organic chemists. So we can put them on a scale of hydrogen bonding and see how strong they are as hydrogen bond acceptors. So here we go back to that first example, drawn a bit differently here, ruthenium tetrakis trimethylphosphine. And here I've drawn the ligands as FHF. So we have a choice in how we describe these. We could describe them as metal fluorides, hydrogen bonded to HF, or as complexes of FHF. And if we look at the X-ray, the FF distance is 2.32 angstroms, a bit longer than we had for the bifluoride ion. That was 2.26. Here's another example with platinum. So these have hydrogen bonds which we imagine are pretty strong, and because of that, we can see the molecules distinctly in the NMR spectra in solution. We can see directly the FHF ligands. Now, that's not always the case, and I'll show you in a moment how we can use that. So if we go instead of the ruthenium to nickel, here we have some square planar nickel complexes with a fluoride on them. And the first thing to say is that the fluorine NMR shows a very strongly upfield shifted resonance for that metal fluorine. In fact, it comes at minus 371 parts per million, coupled to the phosphorus and one of the other fluorines. So this is so well separated from all the other fluorine resonances, we never get any overlap problems. And it's incredibly sensitive to the hydrogen bonding, whereas all the other resonances, whether fluorine, phosphorus, or proton, are not sensitive at all. So this complex and ones like it are soluble in toluene, and what we observe is rapid exchange between this molecule and the complex that is formed by hydrogen bonding. I'll show you that in a moment. So we're working in what we call the fast exchange limit, where we have such rapid exchange that we only see an average in the NMR. The molecule only has one fluorine. You might think, we would study hydrogen bonding with lots of fluorine ligands, but that only makes life much too complicated because you can have multiple interactions. So for preference, we have just one or two fluorines in the molecule. There's the crystal structure, by the way, a square planar diamagnetic complex, and nickel fluorine bond length 1.856 angstroms. So I'm going to do some comparisons, and we have this nickel fluoride that I've just talked about, and some pretty close analogs with palladium and platinum. We can change the phosphines to a certain extent. So this is our series for group 10, and they all have that high field chemical shift. Then we have some group 4 complexes, bis-cyclopentadienyl metal difluoride for titanium, zirconium, hafnium. Here we have our 2 fluorines. They have a D0 configuration as opposed to D8 for the nickel, palladium, platinum. And with D0 configurations, the fluorine resonance is not shifted upfield, but comes in a much more familiar region. So now we can do that experiment to measure the strength of the bonding. So here's one of these nickel complexes as before, and the hydrogen bond donor is 4-fluorophenol. There's a reason for choosing that. It's one of the standards for organic chemists' hydrogen bonding, so it gives us a good comparison. So that forms a complex, hydrogen bonded complex, and that's at rapid equilibrium. So what we do is that we titrate the 4-fluorophenol with the nickel fluoride and see what happens to the chemical shift. And what you can see here is that as we move from a molar ratio 0 to 3 to 1, the chemical shift changes by about 30 ppm. In fact, to be precise, 29 ppm. And the lower curve is room temperature, 300 K. As we cool, the interaction moves the equilibrium to the right, and so we get bigger shifts. So we fit these curves, and at room temperature, we find the equilibrium constant here is 2,800 plus or minus 100, and the chemical shift for full conversion would be 29 ppm. So we can do that fitting as a function of temperature, and we get the enthalpy and the entropy, a simple Van 't Hoff plot. Enthalpy here minus 37 kilojoules per mole, and entropy minus 56 joules per mole per Kelvin. So putting two molecules together, of course, is entropically unfavorable. So now we have some data on the strength of this hydrogen bond. And we can change the hydrogen bond donor. Here we have 5 different hydrogen bond donors, and varying from diphenylamine to hexafluoroisopropanol, and the equilibrium constant changes by a factor of 1,000. So please don't say, oh, hydrogen bonds are always worth about 5 kcals or something like this, 20 kilojoules. They vary immensely in strength, and you can choose where you want to do your reaction. Now, I'm not going to go over this in detail, but what we wanted to do was put these metal fluorides on a standard hydrogen bonding scale. So these scales typically have a parameter for Lewis acidity for the hydrogen bond donor, that's alpha, and another one, beta, for the hydrogen bond acceptor ability, the Lewis basicity. So we want to work out beta for these metal fluorides. And my colleague in this, Chris Hunter, has developed the scales. You can look those up. There's a solvent correction in here, which enables you to compare across different solvents. So I want to move to the results and show you what you see. So what I've got here is a plot of the beta values we determine for those group 4 complexes and 3 of the group 10 complexes. And what you immediately see is that the nickel, palladium, and platinum complexes are much, much stronger hydrogen bond acceptors than the group 4 complexes. That might be counterintuitive at first, but you can think about that one. I'm not going to go into explanations now. The strongest of all is the palladium complex with a beta value of almost 12. So let's go to the standard organic hydrogen bond acceptors and see how they compare. We start here with pyrrole and aniline, around about 4, astanitrile perhaps 5. They're pretty similar. Astanitrile is pretty similar to those group 4 complexes in strength. But to find a hydrogen bond acceptor as strong as those nickel, palladium, platinum, we have to go to the strongest neutral donors in the book. There are none that are stronger than this that I've discovered. Trimethylamine oxide is the strongest at about 11, so that's comparable to the palladium. So what we can, what we can work out from this is, first of all, we can get a quantitative measure of the strength. This clearly relates to the polarity of the metal fluorine bond, and we can see that these group 10 metal fluorides are really outstanding hydrogen bond acceptors. So if you want to build systems with hydrogen bond acceptors, look right at the right-hand end of the transition metals, not the left-hand end. So I want to move now to halogen bonding. So I put in this picture that I took at an exhibition last year for the centenary, sorry, the 150 years of the periodic table. This was a beautiful exhibition in Cambridge, and as you can see, the glass had been covered with transparent stickers for the halogens, including How many of you know what that is? TS, Tennesseum. If I've got it right, that most of us can get as far as astatine, but not beyond. So, halogen bonds to metal fluorides. First of all, I need to explain what a halogen bond is. What we have in a hydrogen bond is an AH unit polarized with the hydrogen delta plus bound to a Lewis base polarized with Y delta minus. In a halogen bond, the base part is the same, but the Lewis acid part involves a halogen AX delta plus. Now, you might think that halogens aren't usually polarized delta plus, but particularly iodine can be polarized that way, and we'll see how that works in a moment. So, a halogen bond, we have an AX interacting with YB. And this is, here you will find the official IUPAC definition, and the definition of the halogen bond, it's sometimes written as an X bond, parallels exactly the definition of the hydrogen bond. But I've summarized it already, so I won't go over the definition now. So if we want to understand what's going on, one of the prototype molecules is iodopentafluorobenzene. And in this molecule, the fluorines are all polarized delta minus, but the iodine, at least in part, is polarized delta plus. And what you find in calculations is here's this iodine on the left, shown in blue, and at the tip, and that represents the region of the potential energy surface that is polarized positively, and that interacts with the Lewis base. This is called the sigma hole. This is one theory of how halogen bonds work, developed particularly by Politzer. There's still controversy about the role of covalent interactions here, and you can read more about that if you want to. I'm not going to talk about the theory today. So, as some examples of halogen bonds in action, I've got three that don't involve metals. This is a 6-stranded DNA. And here we have a ring in which we have oxygen to iodine contacts. So here we have the phosphate oxygens interacting with an iodine because the DNA has been iodinated. So we form that sort of ring there through the iodine-oxygen contacts. The next example on the right here is a catalytic example involving organocatalysis. So here we've got an initial molecule with a carbon-chlorine bond, and we're going to form a carbon-carbon bond which comes from this alkene or and form the carbon-carbon bond there. And the catalyst is this organic molecule with 2 carbon-iodine bonds. And you'll see that these rings, these benzimidazolium rings, are positively charged, and that brings that positive charge in part onto the iodine, which can form the halogen bonds to the chlorine in the original substrate. So that's a catalytic example. One more example. Here we're talking about molecular recognition. It comes from Paul Beer's group in Oxford, where he has a rotaxane molecule, which has here at the bottom, the X is iodine, and they interact with halides that are added. And what you see is that the interaction with iodide is much stronger than bromide, than chloride, because of the halogen bond. So there are some examples of halogen bonds in action. So what I want to do is move to measuring the strength of halogen bonds. And to do this, we use exactly the same principles as for the hydrogen bonds. So we have group 10 metal fluorides, and this time we're adding iodopentafluorobenzene. And we work out the strength in the same way. This is a plot of the enthalpy, delta H, and what you see, rather, I've written it so that it starts from 0 and moves to -25. So the strongest interaction there is with the platinum, a bit stronger than palladium with nickel, according to the enthalpy. If you look at the equilibrium constants at room temperature, it's actually palladium that wins out by a little way over the platinum. So in other words, the one which is the winner depends on the temperature you choose. Remember, we have enthalpy and entropy contributions, so it's inevitable that this varies with temperature. These equilibrium constants are considerably smaller than the ones you saw for the hydrogen bonds. So these interactions are not so strong in terms of equilibrium constant. And this is partly thanks to the very big unfavorable entropy contribution. Nevertheless, we can see the same sort of chemical shift changes in the NMR spectra. So we can also do some comparisons with other halogen bond donors. So here we have our C6F5I, the aromatic one, and the comparison with an aliphatic donor, iodoheptafluorobutane. And we've also got an example here with bromine instead of iodine. So what we find is that the aliphatic ones are stronger than the aromatic. So here we have C6F5I, here we have the butane-derived donor, and that's considerably stronger. What we've also done is put a dimethylamino donor onto this pyridyl ring, and that helps the interaction quite a lot, as you can see. That's the red set, considerably stronger, so that now the equilibrium constant, this is at 283 Kelvin, is about 33. As for using bromine instead of iodine, that's very, very weak indeed. So this little tiny column here is for the C6F5Br, and that's measured at lower temperature, 189 Kelvin, to help the equilibrium along. And even so, it's so small you can barely see it. So iodine is strongly preferred. Now, we can use this idea to build crystals where we have the interactions in the crystalline state rather than looking in solution. And to do this, go back to an idea I mentioned at the start. We use self-complementary molecules. So we have to design our molecules right, and of course, synthesize them. And if we want to do this, we've got to remember that there are lots and lots of interactions that make for a crystal. All the molecules in the crystal have to interact with one another somehow. So if we want to look at hydrogen bonding or halogen bonding, we've got to make sure that that is the dominant interaction compared to the rest. So here's how we do it. Self-complementary interaction with these nickel complexes. So here's the first one for hydrogen bonds. We've got a nickel fluoride as before, but now we've got an NH2 group in the 4 position on that pyridine. So that's set up to form a hydrogen to fluorine interaction. In these examples, we have a nickel halide. It can be any of the halogens. And then we have an iodine in the 4 position of a phenol substituent. So that's set up to have iodine to X interactions. So this design actually worked first time, so unusual for synthesis. Here's the reaction that led to the compound with the amino group. We start with nickel cod twice, the phosphine, and 1 equivalent of the pyridine with the NH2, and that gives us carbon-fluorine bond activation to form the product. And the crystal structure shows a nice hydrogen bonded chain. So here red is nickel, green is fluorine, then we have the NH2 group with nitrogen in blue, and we have this hydrogen bond interaction dominating the crystal structure. The same principle goes for the halogen bonds. So this time we have the nickel fluoride with the tetrafluoroiodophenol group, and the iodine in the 4 position, set up for the halogen bonds. And this forms this linear chain. Here, green is nickel, magenta is the start that again, sorry. Green is fluorine, the magenta is iodine, and there we have that interaction. This distance between iodine and fluorine is 2.655 angstroms. So we can work out whether this is significantly shorter than the van der Waals distance or not. So there are 2 measures of van der Waals radii. One comes from Alvarez and one from Bondi. And the result is that the distance corresponds to, in one case, 76%, in the other 77%, or the sum of the radii. So that represents a great deal of compression, 23 or 24% compressed compared to what we would expect for van der Waals radii. So this offers good possibilities to build into other crystal engineered structures. So just check how I'm doing for time. The last section, I want to talk briefly about interactions of sigma complexes. So now we're talking about interactions between ligands in the primary coordination sphere and how they influence what's going on. So I'll explain more as I go along. Here we have a metal, a ligand which forms a sigma complex XH, and another ligand Y. And here we have the hydrogen interacting with Y. So here's an example. We have a metal and a silane complex. We would call that an eta-2 silane, where the silicon hydrogen is bonded to the metal. And we have another ligand, methyl, and that interacts with the hydrogen. So this is a metal eta-2 silane methyl complex. Now, all that has to happen for this to isomerize is for that silicon hydrogen bond to stretch and the carbon hydrogen interaction to compress. And then we've transformed it into a metal silyl with an eta-2 methane as a ligand. So metal eta-2 methane silyl. So that is often a dynamic process, and that's crucial to the reactions I'm going to talk about. So just a word about sigma complexes in case you're not very familiar. Here are 4 half-sandwich sigma complexes, one with a silane, SiH, bound to manganese. And the point about this is that both the hydrogen and the silicon are in bonding distance to the manganese. So we have an interaction which it requires synergic bonding with the SiH sigma bond acting as the donor and the SiH antibonding orbital acting as the acceptor. The same principle applies to dihydrogen complexes. They're probably more familiar. And to borane complexes, here we have borane BH attached to manganese, and to alkane complexes. This is a pentane complex bound to pentane bound through the terminal CH bond to rhenium. These days, they're nice crystal structures of metal alkane complexes synthesized by my colleague Andy Weller, if you want to look at examples. So I want to look at the interactions between the ligands, as I showed a moment ago. So here are 2 examples. We'll start at the left here with the iron. This is one of the early examples. And here we have an iron with 2 hydride ligands and a dihydrogen ligand. And the other 3 ligands are phosphines. And what we see in the neutron diffraction structure is that there are 2 quite different interaction lengths here. The H2 bound H2 has a bond length of only 0.82 angstroms, but the hydrogen here interacts with its neighboring hydride with a distance of 1.86 angstroms. So there's certainly an interaction between these 2 as well. Now let's look at this rather more complicated molecule. This is a ruthenium complex with disilazane ligands. They're all 3 chelating ligands are identical, so I've simplified it to this picture here. And what we find is that this silicon that I've labeled A has a short silicon hydrogen interaction, 1.874. That would be an eta-2 silane interaction. But that hydrogen there interacts with its neighboring silicon, B, that length is 2.099, but it does not interact with the 3rd silicon, C. That distance is far too big to be significant, 3.03 angstroms. So in other words, we have 1 relatively short silicon hydrogen, 1 a bit longer, there's the interaction, and one which is distant, not interacting at all. And I've chosen these structures because they are again determined by neutron diffraction in both cases, so we're very confident about the positions of the hydrogens. This one goes back to Odile Eisenstein and Ken Colton. This one here on the right comes from Sylviane Sabot-Etienne's group in Toulouse. So what can happen now is that we can use this principle for reaction. So these are metathesis reactions, and to begin with, I've written them in terms of X and Y, where X and Y are either hydrogen, boron, or silicon. And what we're trying to do is to convert a metal X bond to a metal Y bond. And we do this by reaction with YH. Now, the typical mechanisms of the textbooks are oxidative addition and reductive elimination. That's shown at the top, where you change oxidation state and you cleave the YH bond. That's one mechanism. Another is called sigma bond metathesis, typical for D0 complexes, where we simply form a four-membered transition state, no intermediates at all, to yield the product. But what Sylviane Sabot-Etienne and I worked out was that if you can form these sigma complexes, we've got an alternative route. So here we have that YH bound to the metal as forming a sigma complex interacting with X. We do that little dance as I described before, and now we have HX bound to the metal. We lose that HX and we've got to the product. So these isomeric sigma complexes open up the route to metathesis, and we call this sigma complex assisted metathesis or sigma CAM mechanisms. So over the years since we proposed this way back 2007, it's turned out that this mechanism is very significant for reactivity of alkanes and of hydrosilanes, and even simple reactions like the metal methyl reacting with hydrogen, hydrogenolysis, cyclometallation. So I'll just show you one example to finish with, the metal methyl hydrogenolysis. This work comes from Maurice Bruckhardt and Ernesto Carmona's work published in 2013. And again, I will simplify it down to begin with. So we have a metal methyl that reacts with H2 to form one of these sigma complexes. So we now have metal dihydrogen methyl, and that can isomerize to metal hydride methane. Lose methane, and we've made a metal hydride. So that's the sigma CAM reaction mechanism in action. The metal Ln here is an iridium hydride pincer cation here. So in reality, this has 3 hydrogens attached, one from the original MLN and then 2 more. How do you know that's the right mechanism? Well, the first thing is deuterium exchange, and that deuterium exchange into the methyl and the terminal hydride occurs at exactly the same rate. So they must be exchanging. Then you compare the free energy barrier from experiment and theory. They're the same within 1 kilojoule per mole. That's astonishingly good modeling. And the structure of the transition state, indeed, here it is, corresponds to what you'd expect with that methyl group and the hydrogens and the interaction. So this mechanism depends on the secondary interactions between the ligands. So just to finish off, these secondary bonds can, of course, be detected in solution and solid states. In favorable cases, we can measure the bond energies. As I've mentioned, the energetics vary enormously. We can design with stronger secondary bonds or weaker. We need to think about the energetics, not just say, oh, well, let's have a hydrogen bond. So we can design that into our synthesis. And these secondary bonds have a huge influence on the structure, on the catalytic mechanisms and barriers to reactions. And that's what I've really tried to emphasize, the effect on catalysis. So just to finish off with, I'd like to thank my collaborators, and here 4 collaborators in different universities: Lee Brammer in Sheffield, Chris Hunter now in Cambridge, Odile Eisenstein in Montpellier, and Sylviane Sabotienne in Toulouse, and also the people who worked on these problems in York, especially these were 7 people: Dan, Vardini, Lassa, Sarah, Torsten, Adrian, and Pedro. And with that, thank you for listening, and I'll be happy to try and answer some questions.
Thank you very much, Robin, for a very interesting lecture, and as usual, very, very, very clear. And I forgot to say at the beginning when I did the presentation that there is 15 minutes for questions, and the questions have to be written in the chat line. And there is already a question on the chat line that I can read for you. There are 2 questions in the reality. The first is by Shima Shahafar. And the question is hydrogen or halogen bondings in complexes related to complex structures? His explanation is same core metal, different geometries such as square planar versus octahedral.
Right. Just to reiterate the question, what we're concerned with here is whether there's a substantial difference when you have octahedral or tetrahedral structures or square planar.
Yeah.
And I think the answer is no, not a very substantial difference, but the electron configuration and matters a great deal, and the other ligands, the ancillary ligands, also have an influence, because what we're concerned with is the polarity of the bonds. And so I don't see why you can't build these interactions in a variety of different geometries. There's a complication, though, and that comes from how labile the complex is. If the complex is very labile, we may have a great deal of difficulty in seeing what's going on.
Thank you. And there is another question by Igor Maldonado. And the question is about the halogen bonds. Why the aliphatic molecules show the stronger halogen bonds? As these interactions have a negative contribution from entropy, aromatic molecules shouldn't show stronger bonds, as it costs less to reorganize these molecules.
Right. I'm not sure that I can answer this very satisfactorily. First thing to say is that the same has been found with other halogen bond acceptors. For organic halogen bond acceptors, the aliphatic are also stronger. And as far as the entropy contribution is concerned, there's a substantial negative entropy in each of them. And I'm not convinced that that is what leads to the difference. I think that the difference probably arises from the molecular orbital structure of the molecules and the polarity of the carbon iodine bond. But I can't give you a full explanation with any confidence. I will have to go back to some of the theory papers to answer that question.
Yeah. Thank you. I don't see any other question in the chat. We can wait a little bit. And in the meanwhile, I have a curiosity. Thank you for the answer by Igor Maldonado, by the way. There is a message for you. I have just a curiosity for the last section of your talk when you speak about the possibility that XH sigma complex is the H interact with another ligand in the molecule coordinated at the metal. I wonder if they are enough stable, if it is possible to detect this interaction by looking at the coupling constant between X and H and Y.
Ah, right.
So silicon this would be not that difficult if you have silicon.
Right. I think the answer is no so far. What you can do is look at the dynamic exchange by NMR. As for hydrogen bonds, looking for couplings across the bond is more difficult. So in those examples, wait a moment, in the examples where we were measuring the bond energy, we have not seen any coupling across the bond. On the other hand, with the FHF complexes, we have seen coupling across the bond. So if you make the interaction strong enough, yes, that is possible. But if you have the examples with dynamic exchange in the fast exchange limit, we can't see the coupling across the bond. But there's one other sort of coupling that we have noticed, and that is if we have a platinum fluorine complex, and that interacts with a hydrogen bond donor like hexafluoroisopropanol, the platinum fluorine coupling constant changes as a result of the interaction. Now, on the face of it, this could be argued to mean that we have a covalent contribution to the halogen bond. But I've looked into this and there are alternative explanations, so it can't be regarded as proof of a covalent interaction.
Thank you very much. Thank you very much. There is a message from Odile, just for information. Be aware that bonds between very electron-rich centers are possible. There is a new theory called the charge switch bond, which describes this. This is a proposal that hydrogen bond should be associated this way. This is, I don't know if you comment on that. I don't have anything to say.
I think it's better if Odile comments on this, because actually Odile has sent me these papers in the last few days, but I have been so busy preparing this lecture that I haven't read them yet. and but what I would stress to you is that the sigma hole theory is not the only explanation of the halogen bond. There are alternative explanations, and also I would stress that this sort of secondary interaction is very characteristic of heavy elements, so it can be extended to elements adjacent to iodine in the periodic table, like tellurium, or and when you look at the structures of these compounds, so even simple compounds of these heavy elements, they often show up secondary interactions as a much more dominant part of the structure than if you look at structures of lighter compounds.
Thank you. I see that Odile is adding something perhaps for all people, saying that the charge shift bond is a resonance between covalent and ionic bonding. So that could be useful, especially for young people. I don't know if Odile would like to add something, or that's all. I don't hear. I'm mute. Okay, Odile is mute, so I cannot. That's okay. You can add something when you will have your lecture.